A voltage to current converter, also known as voltage controlled current source, is discussed in this example in terms of how the circuit is working and how to properly select the value of components in the circuit for a target operation, in which case we are, for example, targeting a maximum 1 amp current at the output of the circuit being provided to a given load RL. So we want to see how the circuit works. We want to decide the value of the components properly, and then we want to target maximum 1 amp at the output of the circuit. And let's consider this scenario for the voltage to current transfer characteristic. So at input we have Vn, which we can control, and then at the output we have Iout, which is provided to RL. And let's say we want to say that our Iout can be between 0 to 1 amp or 1000 milliamp. And say, for example, 1 amp is realized when input reaches maximum value of 5 volt for Vn. So basically Vn moving from 0 to 5 volt. That's the range. So effectively we are trying to realize a sort of a straight line for the V into I out characteristic with a slope of, say, we are talking about 1 amp over 5 volt. So basically we are talking about 200 millisiemens, which means that when input V in is 1 volt, then output current becomes 200 milliamp. When input V in is 5 volt, output current becomes maximum 1 amp. Okay, so for that scenario, how do we design and select the components properly, given that this circuit is a single supply design? Only 10 volt exists in this circuit, and then we have on the other side just ground connection, and that also applies to op-amps. Op-amps are on one side grounded for the one side supply, and for the other side we connect them to 10 volt as well, so that op-amps are biased properly. Okay, so let's start. Now we have the maximum current 1 amp. Let's discuss what are the options. So we have a PMOS or P-channel MOSFET transistor here, and then we have the body properly connected to the source of the transistors. So we have source and we have drain on the other side. Let me use a different color so that it's better visible. So we have source and we have drain and we have the gate. All right, so now we have at source, we have connection to resistor R3 to 10 volt supply, and we have connection to via resistor RF2, which means R feedback, which is then providing a connection to negative input terminal or inverting terminal of op-amp number 2. Okay, which is properly biased and not saturated, so it will enforce via negative feedback, that is in this design for the op-amp, it will enforce the virtual short, which will guarantee that we have the same voltage on negative and positive terminals. So I'm going to write it here. Voltage at negative is equal to voltage at positive terminal for op-amp, which we refer to it as, of course, as the virtual short between the two input terminals of properly biased and operational op-amp. So virtual short. Okay, what is the benefit of that? As I said, for maximum I out, we have 1 amp current that is going through the source drain of PMOS transistors. So I'm going to refer to that as IST PMOS max. In this case, we are saying it's 1 amp. Just bear in mind that in this circuit, obviously, the PMOS is bearing the main responsibility of high current delivery to load. So the PMOS need to be selected properly as a power transistor with the, let's say, at least the minimum continuous current tolerance of 1 amp. So maybe shooting for, when we select this from DigiKey or Mauser, it's better to shoot for a current max of, say, up to 2 amp or in that ballpark, so that we protect this transistor. Okay, so the NMOS or let's say N-channel MOSFET transistor here is a normal transistor. It's not a high power, it's actually a low current transistor. I'm going to show you. So let's say the maximum consumption is in this branch at the output. We will design the circuits in such a way that the consumption here in this N-channel MOSFET and rest of resistor will be minimal for the higher efficiency of the circuit. Okay, so we have 1 amp going here. So the only concern about selection of R3, we have a couple of options, but just bear in mind that the voltage that appears at the output of the load, or VL, or let's say V out, we want to be able to have maximum range for V out. So ideally, we would like to have V out to move or change from 0 to max 10 volt, but that is impossible. We know that we should tolerate some level of voltage drop across R3 and some level of voltage drop across the source drain of the PMOS. So the voltage compliance range, so I'm going to write it here, voltage compliance range at the output of this circuit, we would like it to be maximum. So let's say if the saturation IST sat of the PMOS is, for example, 0.5 to 1 volt for power PMOS, and then let's say something on the order of 0.5 volt to 1 volt is what is just max tolerable for the voltage drop across R3. So let's, as an example here, let's shoot for just 1 volt drop across R3 max. So I'm going to write it here. VR3 max is going to be 1 volt. And with that, given that it's just the R3 times Imax, and Imax is at the output is just 1 amp, so we can therefore decide that R3 is 1 ohm. So a good selection for R3 will be 1 ohm. Of course, you can go down to 0.5 ohm, but just remember that whatever we select for R3, it has to be a power resistor, meaning that it can tolerate a high power consumption. In this case, if we go with 1 ohm, then 1 ohm times 1 amp DC will result in 1 watt. So R3 in this case is 1 ohm and 1 watt. So that should be, so let me write it here. It appears that I can't write that far, so I'm going to just move this guy here, and then I'm going to just move what I wrote. Sorry for the, I think now you can see it. All right, so there you go. So R3 has to be 1 ohm and 1 watt in this case. You can of course go with 0.5, but just bear in mind that whatever resistor you select for R3 needs to be easy to be purchased if you care about practicality of the design. For this resistor, I also recommend we go with 1%, let's say tolerance for the resistor. So those are the spec for the resistor. So 1% is good enough, but I'm going to show that for the less important resistor in terms of the value and power consumption, we better go with 0.1% tolerance for accuracy of the circuit and less sensitivity. Okay, so regarding RF2, there is no current that can go through RF2. That's zero current, 0 microamp, for the reason that on one side is connected to negative input terminal of op amp, so because of infinite impedance, no current can go that way or come out that way. So therefore, and also there is a cap here, CF2, feedback cap, that is mainly for stability reason. So just bear in mind that the combination of CF2, RF2, and RP, or the resistor that is connecting the output of op amp to the gate of P-channel MOSFET, these are just purely for stability of the circuit, nothing directly related to current generation. So in this circuit, R3, R2, R1 are directly just deciding the current value combined with P-channel MOSFET and N-channel MOSFET. Okay, so let's just analyze the circuit quickly. Okay, so at maximum current 1 amp, we have, with 1 ohm resistor value selected for R3, we have 1 volt drop across R3. So that means we have 9 volt at this node, which is the same as negative terminal of the op amp. But then op amp is operating properly. So op amps are biased properly in linear region, basically not saturated, and as a result, negative feedback is enforced, or negative feedback will force the op amp to satisfy virtual short. So forces virtual short basically, which means for the op amps, which means positive input terminal is equal to negative input terminal in a steady state operation. So V plus and V minus are equal to each other. So if, for example, we have 9 volt here, then we should have 9 volt here as well. All this means is since we have 10 volt on one side of the R3 and R2, and we have same voltage on the other side, therefore the voltage drop across R2 and R3 is the same. So what I'm trying to say is plus minus V R2, and let's say, so here, plus minus VR3. So all I'm saying is, because of virtual short for the second op amp, we can write that voltage drop across R2 and voltage drop across R3 should be the same, which means, okay, so the voltage drop across R2 is this current of transistor number 1, which is the N-channel MOSFET. I'm going to refer to it because it's a drain source. So drain on top, source bottom. As you can see, the body or bulk properly connected to the source for the N-channel MOSFET so that it has normal operation, and the gate. So as any MOSFET device is effectively a 4-terminal device, but since we connect the body to source, then it's just a 3-terminal device for us here. So there is an IDS for N-channel MOSFET that is flowing, and that's exactly this current, IDSN. So let's just write it, IDSN. So I'm going to write IDSN times R2 is going to be equal to VR2. And on the other side, we have ISD PMOS, which is the output current effectively, is going to be times R3 is going to be equal to VR3. So let me just summarize that here. Okay, so what do we have? For VR2, we have IDS N-channel MOSFET times R2, so that's this resistor, equal to, for the other side, we have ISD for P-channel MOSFET times R3. And remember that I said this guy is the same as I out. So I can say, therefore, IDS N-channel MOSFET times R2 is equal to I out times R3. Okay, so we are almost there. So effectively, in summary, what I'm trying to say is I out is equal to R2 over R3 times IDS for N-channel MOSFET. So let's refer to this as equation 1 in this design. Okay, so next step. How do we select the value of, let's say, this current IDS for max? Because we are talking about the scenario in which the maximum current in this output branch is 1 amp. And then we need to decide that for that case, what is the value of maximum current for the N-channel MOSFET? So, as I said, the main responsibility of delivering current and burning power is in the final branch. To sort of make sure that this circuit is going to be able to deliver an efficiency of, say, for the conversion of the voltage to current, efficiency of around 99% or even better, I'm going to enforce by the design such that when we have 1 amp going through the final branch, this current here is going to be 1 over 200 of that current. If it is 1 over 100, then the DC consumption is 10 volt times a current that is 100th less than this one. So it will sort of get close to 99%. But for better than 99% efficiency of conversion, so let's say higher than 99% conversion efficiency in this circuit, then I am going to set the IDS of N-channel, which is the current going through the sort of internal branch, is going to be equal to, say, as a good design choice, 1 over 200 of the output branch, which is the current of the going through the ISD of the going through the source drain of the P-channel MOSFET. All right, so the maximum for this guy, so if you're talking about max then it will be 1 over 200 times the max current, which is 1 amp. So we are talking about 5 milliamp. All right, so if I want 5 milliamp maximum current, then we can decide the value of R2 as well, because we know the voltage drop. Because as I said, when we have 1 amp going through the R3, given the 1 ohm, the voltage drop is just 1 volt. So therefore, we can just say, therefore, R2 is simply equal to, so it's just decided, right? We can use equation 1 because what I'm going to say is repeat of equation 1. So in the equation 1, we are saying 1 amp for I out. And then we are saying equal to R2 need to be decided. But R3 is just 1 ohm. And we just found that in equation 2, we found that IDS N max is 5 milliamp. So basically this guy is 5 milliamp. So that defines the current, the resistor R2 to be 200 ohm, which is a very good choice in terms of availability. All right, so recommendation is the value of R2 is 200 ohm, and for the sake of minimal sort of sensitivity of the circuit to variations, then we're going to select this resistor because it's a low power resistor. It's not a high power resistor, and it's a reasonable value, 200 ohm. We're going to select it 0.1% tolerance. All right, and what about R1? How do we select the value of R1 that way? Well, we are there. Now that we know what is the IDSN max, which we just found to be 5 milliamp, remember that we want the maximum current of 1 amp, or basically we want the IDS 5 milliamp to happen when input is 5 volt. So let's go to input. If input is 5 volt, and look at the op-amp 1, it's properly biased, virtual short is going to be there as well. So positive and negative terminal of op-amp have the same voltage. So if we have 5 volt here at positive terminal, then by virtual short, we have 5 volt here at negative terminal as well. And for the same reason discussed, there is no current going through RF1 in steady state DC because there is no route for the DC current to flow, because nothing can go through or come out of the input terminal of op-amp because of infinite impedance. So that 5 volt will be here as well. Nice. Okay, so for resistor R1, we know that there is 5 volt here at max for the maximum range of Vn. And then we know that at that point, the current, which is the same current coming down, basically the IDSN current, we know that that current is 5 milliamp. And then the value of decided right clearly. So 5 milliamp times R1 will give us 5 volts. So R1 has to be 1 kilo ohm. So I'm going to write it here. So we have VR1 equal to I drain source N-channel MOSFET times R1. And we know that this guy has to be 5 volt. So that's the max range of, so I'm going to write it here in parentheses. So V in max, basically. And for IDSN, we know that its maximum value is 5 milliamp as decided in equation 2. So therefore, that gives us the value of R1 to be 1 kilo ohm. Again, it's a very low power resistor, nominal resistor, good choice in terms of the value. I highly suggest that we go with 0.1% tolerance so that we minimize sensitivity of the circuit to conversion, basically. So we have an accurate conversion from the input voltage or voltage that is controlling the output current. All right, so we basically decided about the most important resistors in terms of the conversion, and we can actually find the formula as well. So let me just formulate the problem now. So it's going to be, okay, so with R1 known, what happens is we always know that because of the way things are designed, no current can go through these guys, no DC current. So whatever V in comes in, that V in will appear across the resistor R1, and therefore the current IDS1 will be defined. So I'm going to say that the current IDS or of the N-channel MOSFET will be always equal to V in over R1. So now combine this equation 3 with 1. So 3 with 1. And we basically just get the final formula. So I out equal to R2 over R3. And then we are substituting IDS n with this value here. So R1 Vn. That is the positive conversion coefficient, which is effectively just a so this guy is a transconductance. It is converting voltage to current. So it's the ratio with a dimension that is with a unit that is Siemens or mu, inverse ohm or ohm inverse. Okay, so it's a positive value and is exactly satisfying what we discussed over here in terms of what we are chasing for the voltage to output current characteristic, and it is exactly satisfying what we need with the values selected. Okay, so last note, op amps 2 and 1, they are just a nominal op amp. So you don't need to go after high current op amp. Just the only thing that is important about these op amps is they need to be, so I'm going to write it here, op amps recommended to be, let's say, CMOS op amps, so that input current is absolutely very small, very low offset or zero offset, and also very low drift, so that over temperature and over time, the value of offset at the input of the op amp is going to be minimal. That way, we guarantee the stability of the circuit and accuracy of the operation. So that's one thing. You can take a look in either DigiKey or, let's say, a Mauser to select among the many choices they have, just a low power op amp, just as I said, either zero offset or very low offset with low drift. That's the main requirement for these op amps. For the value of RNCF1 and RF1, which are basically a stability component in the circuit, let's say for Rn and also at the same time Rp, which are basically just separating the output of op amp from the input capacitive load of the gate of the MOSFET transistor for a stability reason. So the value between 200 ohm to 400 ohm are just good choices in general. You can play with them. So these are not necessarily things that we can have and write equation for them, but depending on what PMOS, NMOS you end up selecting, which as I said, be careful that for PMOS, it has to be able to tolerate continuous maximum current of 1 amp and voltage of a source drain up to 10 volt, which are very reasonable values. Nothing strange about them. But when we select them, then based on that, we can play with the value of the resistor Rp for the stability reason in the circuit to make sure circuit is stable, no oscillation, no weird behavior, no ringing. And the same thing for Rn, we select the value properly, except that the NMOS or N-channel MOSFET here is very low current. So there are many choices for that one. Okay, so for CF1 and CF2, the feedback resistors that are effectively connecting the output of op amp to, say, negative input terminal for both scenarios, for both op amp 1 and 2. This is mainly for the case that, again, it brings a stability to the circuit. It just the fact that at high enough frequency of, let's say, noise or whatever high frequency component that we are analyzing, because the impedance of cap is 1 over j omega. As the frequency is increasing, j omega c. As the frequency increasing, the impedance dropping. So at some point, effectively, for some high frequency component, CF1 is short. What it does, for those frequencies and above, it directly connects the output of op amp to negative input terminals, sort of acting like a buffer. And with that, it will just basically forces same voltage at gate for those frequency that similar to source. So basically VGS is enforced to 0, transistor is shut down for those currents, and basically nothing pass to the output of the circuit because effectively for those components MOSFET is not responsive. Okay, so that's for stability reason. The time constant will be defined by combination of or the product of RF1 CF1 mainly, if that matters in a design. But generally speaking, I would say both CF1 and CF2, 1 to 2 nanofarad, are good choices in general. And for a stability reason, you can play with them. And RF1 and RF2, a good choice for that would be some value in the range of 5 to 10 kilo ohm. So these are just a general value to define a good stable circuit that is reliable design. This way we get a conversion accuracy of better than 99% because the power consumption in this branch is going to be extremely small compared to the actual power consumed in the final branch. And the circuit is just using low power, as I said, low drift op amps, so we are not concerned about the power consumption in these op amps as well. All right. So I'm hoping that this sort of a quick review of what is needed to be done in this circuit is helpful to see how a practical voltage controlled current source, or basically voltage to current converter, can be designed and analyzed. Thanks for watching.